Folks, here is the homework solutions for the questions that I was asked about the Unit 5 Day 1 homework. The first one, page 90, number 1F, this uses the chain rule, which I'm unsure why this was in this section, because the chain rule isn't taught until a later part of the unit. But in any case, just skip this one for now and we'll look at that later this week. Number 2, we've got page 90, number 12. Now, we want to find the quadratic function ax squared plus bx plus c if its graph passes through the point 2, 19 and has a horizontal tangent at -1, -8. So we've got some information here. We know that if this is a point on the function, then f at 2 is equal to 19. If it has a horizontal tangent here at x equals 1, then we also know that f prime at -1 equals 0. That's the derivative or the rate of change at that point. But it also gives us the y value. So we also know that f at -1 equals -8. So we can start with what we know about the derivative maybe. We would know that the derivative of this function will be 2ax plus b. And the c, of course, will disappear. And then f prime at -1 is 2a times -1 plus b. And we would know that that was a horizontal tangent, so that 0 equals -2a plus b, or b equals 2a. So we've got that relationship there. From the other two pieces of information back here, we know that f at 2 equals 19. So 19 equals a times 2 squared plus b times 2 plus c. So 19 equals 4a plus 2b plus c. And then similarly for the -8, -8 equals a times -1 squared plus b times -1 plus c. So -8 equals a minus b plus c. I'm going to take each of these, and we kind of want to get a system of two equations and two unknowns. So I'm going to sub in b equaling 2a into each of those two equations. So I'll call that 1 and 2. And then for 1, I'm going to have 19 equals 4a plus 2 times 2a plus c. 19 equals 4a plus 4a plus c, or 19 equals 8a plus c. And then in equation 2, pretty similarly here, I get -8 equals a minus, and b is equal to 2a plus c. -8 equals -a plus c. So then I've got these two equations, and they're lined up pretty well for elimination if I wanted to subtract those. Kind of running a bit tight on room, but I can fit this in. So if I have 8a plus c equals 19, and then -a plus c equals -8, and I want to subtract those to eliminate the c's, here I get 9a equals, and that'll be 27, so a equals 3. Then we know b equals 2a, so b is 2 times 3, b is 6. And then from either one of these two equations up here, we can say that, let's say c, from that second equation, I'll just rearrange and say c equals -8 plus a, bring the a to the other side, c equals -8 plus 3, so c equals -5. So my function, just kind of summarizing, I'm going a little bit all over the place to fit on one page. We've got 3x squared plus 6x minus 5. And you could redo the derivative now with these values. Do kind of a double check that, yes, what happens if you sub in x equals 2? Do you get 19? If you sub in x equals -1, do you get -8? And then take the derivative of this function and double check that it would have a horizontal tangent at that -1. Okay, so here we have an exponential function f at t. We want to determine the value of t where the derivative is 0. So we'll find the derivative here. So I'm going to do the first factor, so 10 to the 3t minus 5 times the derivative of the second, which is e to the 2t squared, times the derivative of that exponent, which is 4t, plus the second, so e to the 2t squared, times the derivative of the first, which is 10 to the exponent, keeping the exponent the same, times that ln 10, which is our adjustment factor, times the derivative of the exponent, which is 3. And maybe I'll put that in brackets because that looks a little... So hopefully that's clear. And then we're going to want to factor, but I'll clean this up a little bit first. So I have 4t, 10 to the exponent 3t minus 5, e to the exponent 2t squared. And then here I have plus 3 ln 10, 10 to the exponent 3t minus 5, and e to the exponent 2t squared. So I have common factors here. That's a common factor, 10 to the exponent 3t minus 5, and e to the 2t squared. Remember that we are going to really want to start factoring our answers to be able to find those zeros of the derivative, because those turning points are really important. So I'm going to pull out these common factors. And what I'm left with is 4t plus 3 ln 10. And ln 10 is just a numeric value that you can figure out on your calculator. So when I'm looking at these, so this first factor, 10 to any exponent, that will never be negative and never 0. There are no values for that exponent that if you do 10 to some exponent, you get 0. It's never 0. And if you think about our exponential function, it never crosses the x-axis. And same here, this will be never 0. So it's always greater than 0 for both of those. They're always greater than 0, those exponential functions like that. They never cross that x-axis. So the only one that could be a 0 is here. If 4t plus 3 ln 10 equaled 0, then t would equal -3 ln 10 over 4. So that's the value that gives a derivative of 0. T equals -3 ln 10 over 4. And you could do that on your calculator if you wanted to get a value. So here we're looking for the derivative of this function, and I would kind of group it like that personally and look at my two factors. So here, dy dx. So I'm going to take the first factor, 3 sine 5x, times the derivative of the second. So the derivative of tan is 1 over secant squared of 5x times the derivative of the angle, so times 5. And then plus the second, which is tan 5x, times the derivative of the first. So this would be 3 cos 5x times the derivative of the angle, which is 5. And then probably what I think people are more likely having trouble with is how to clean this up. So Oh, I don't know why I did, sorry, 1 over secant squared. I was thinking of making that 1 over cos right away. So this is just secant squared, 5x. So here we've got 15 sine 5x secant squared 5x. And then plus, and this is the same idea here, 15 tan 5x cos 5x. So I feel like there's likely, and I'm looking ahead a little bit, I don't like having that secant because I feel like we could probably simplify. Also tan, because I've got a sine here, I'm going to write this as sine over cos. Just to simplify this a little bit, I would get everything in terms of at least sine and cos. So 15 sine 5x. And here is where I'll do 1 over cos squared 5x plus 15 sine 5x over cos 5x. And there's different ways that we could leave this, but definitely simplify out and get rid of secant. Here, get rid of tan because then those cosines will cancel. I don't know how they've simplified this in the book, in the answer, but I would probably factor out a 15 sine 5x, and then I would say that's 1 over cos squared 5x plus 1. And there's different ways of looking at that because of all the trig identities. You could really have a number of different ways of writing this. But here, if I was kind of looking ahead, I would be able to find zeros there, and I would be able to find zeros there by solving each factor equals to 0. And that's kind of your goal. Okay. This one's kind of similar, but here we're looking for the second derivative. So dy dx. And so the first is sine x times the derivative of the second, secant squared x. Plus the second, so tan x, times the derivative of the first, which is cos x. Now, in order to do the second derivative, we're going to have to clean this up because, in particular, we don't know the derivative of secant, especially secant squared. So here, sine x over 1 over times 1 over cos squared. And here, I remember what happened when I did this. That actually cleans up really nicely. That will just be sine. Now here, when I have sine over cos squared, I don't know how to do a squared, and I don't know how to do stuff in the denominator. So what I'm going to do is take one of the cos squareds on the bottom. Actually, you know what? I was going to write this as like tan x over cos x plus sine x. And you know what? We are a little bit stuck here because that is a fraction. I thought this looked like it would only have product rule, but I'm going to stop there, and you guys are going to look at quotient rule today. So we'll stop at just the first derivative there. But after Unit 5 Lesson 2, you should be able to finish that one up. Here, determine all the values of x for between 0 and 2 pi for which the slope of the tangent f at x equals sine x tan x is 0. So I'm going to go back because this is actually the same function. And the the values here, I'm just going to kind of take from here that this would be sine x times 1 over cos squared x plus sine x. And that's the exact same derivative. So f prime at x is sine x times 1 over cos squared x plus sine x from previous slide. Okay. If I want to make things equal to 0, factoring is always a good idea. And then we would want to look at where sine x would equal 0 and where 1 over cos squared x plus 1 equals 0. So we know in the first cycle that this would be 0, pi, and 2 pi, where sine x equals 0. That's kind of the easier one. Here, 1 over cos squared x equals negative 1. Uh, 1 equals negative 1 cos squared x, or cos squared x equals negative 1. So here we have to kind of look at this, and there's no way to square the value of cos and get it equal to negative 1. So that would be no solutions for that factor. So the only places where this derivative would be 0 would be where sine x equals 0 at 0, pi, and 2 pi. And that is it for today's homework questions.